this is really the problem, that phase matching for second harmonic generation unfortunately is not an easy gift from nature. You see, for normally dispersive media, the refractive indices correspondingly at omega and 2 omega are expected to be different. So, we can never generate SHG, it seems, right? Is that the case? But then we already said that someone tried their hand at second harmonic generation and even published a very nice paper, but the paper did not contain the data evidencing the second harmonic. That was not because they did not see the second harmonics. The editing process removed, what was maybe mischief in history that this thing went away, but there are countless accounts of doing second harmonic generation, right? And I have myself papers where maybe if not second but third harmonic was either generated or used in the process of doing experiments. We do that routinely in our lab. So, as I said, we can take you through and have you do a little demonstration for you as well. Now, can we never achieve second harmonic generation, or if we can always have SHG, which is true, which of the two is true? But as optimists, so I would say that no, we can always generate second harmonic. We can always do this because we are physicists, we are engineers, we are we think out of the box and try to figure out solutions, right? So, second harmonic generation is possible, but we need to appreciate some more optics for that, okay? Or as our colleague here said, we need to invoke another nuance in optics, okay, so that we achieve the phase matching condition. Remember, what we are trying to achieve is phase matching. Here for us, that means n at omega 1 should be equal somehow to n at twice omega 1. Somehow, but how? So, optics comes to our rescue. Optics and crystals come to our rescue. Okay. Whenever we have a crisis in physics, like now we want to unify quantum mechanics and gravity, or the community is thrown up a surprise in the form of, say, dark matter or dark energy or whatever. What do we do in physics or in science? We go and examine the roots, the fundamentals. Okay, I am sorry that the J somehow is not in the subscript. So, these are EJs. So, let us go back to the roots and examine the most fundamental equations that we have in our kitty. We have Maxwell's equations, but the 4 Maxwell's equations do not capture, or they do not model the physical medium in which the light wave is propagating. That is left to the constitutive relations. We have non-magnetic media. So, B is equal to mu H plus M. We do not need to bother about that because M is 0 in that constitutive relation. All we need to rethink deep about is D is epsilon naught E plus P, okay. But then P is what? P is epsilon naught times chi 1 but times E. This is a vector relation written component wise, but chi is now a second rank tensor. It is not necessarily a scalar. In an earlier lecture, I enunciated the fact that chi ij is a 3 by 3 matrix. Chi 1 1, 1 2, 1 3, 2 1, 2 2, 2 3, 3 1, 3 2, 3 3, but it is symmetric. So, it has only six independent elements, because okay, this is chi 1 first order chi, chi 1 of I j is chi 1 of j I. It is a symmetric second rank tensor, and we said that this symmetric second rank tensor can be diagonalized, so that it is a diagonal matrix with 3 diagonal values: chi 1 1, chi 2 2, chi 3 3. If the 3 are equal, then I can write it as a scalar. I can simply say, in this case, P I is epsilon naught chi 1 times E I, or else the most general way of writing down this expression is to have chi, the matrix chi 1 I j, or let me just call it chi I j for now, mediate the transfer between E j, transaction between E j and P I. Okay. The summation over the repeating index j is implied in these expressions. Okay. So, substitute for this in d, di is epsilon naught 1 plus chi 1 I j multiplied by E j. Now, call this factor epsilon naught 1 plus chi 1 I j to be a new epsilon I j. Okay. This is just some maneuver. Epsilon is epsilon naught multiplying 1 plus chi 1 I j. Now, essentially we saw earlier that the real part of the refractive index, or the refractive index, is the square root of 1 plus chi I j, with a slight abuse of notation to absorb the epsilon naught into this milieu, which we can do based on the system of units and the style that we adopt for this. The refractive index is the square root of epsilon I j. All right. What does this essentially mean? This essentially means that refractive index, which was earlier dependent on, we thought to be depending strongly on frequency omega 1 and omega 2, the value for this, it seems that this was never equal. Now, we have a new handle, a new degree of freedom, a new possibility. There is a direction dependence. Of refractive index, which we will understand better in this and the next lecture. But what is this the direction of? Right? That is the question. If epsilon 1 1, I take the diagonal configuration of the epsilon I j matrix, all the other entries are zeros. This, if epsilon 1 1, epsilon 2 2, epsilon 3 3 are the 3 eigenvalues for this matrix, the epsilon I j matrix, which is symmetric and has 6, therefore 6 independent components about some general direction, right, but along special directions, so called principal axes for this system. It is really only 3 numbers that we will have to know to determine the entire 9 component matrix. All this is captured very well in these reference texts. Please have a look at them. The iconic Nonlinear Optics by Robert Boyd, Elements of Nonlinear Optics. I recommend strongly this book. The first chapter of this book is beautifully written. It is like poetry and prose about nonlinear optics. Please read that for a very nice purview. Optical Electronics by Tyagarajan and Ghatak, an excellent treatment especially of what I am discussing now. These phenomena which my colleague here rightly called birefringence, we will soon introduce such a term, and a very nice, I would say, connecting piece between a beginner and these otherwise 3 advanced texts, Boyd, Butcher-Cotter, Tyagarajan and Ghatak, by my co-authored by our own colleagues from IIT Madras, Professor Vijayan and Professor Murthy, Essential Nonlinear Optics. Okay. So, please look into these for a gentle introduction and greater enunciation of these concepts, but for the purpose of this lecture, and today we will close with this, establishing this important nuance that the refractive index of the beam depends on a certain direction. What is this the direction of? The answer to that lies in this parent equation here. The indices I and j are to be viewed as follows. A sketch here is worth literally 1,000 words. So, let me indulge a bit in that. Of course, the indices I and j can take values 1, 2 and 3. So, the coordinate system here, the Cartesian system here is O x1, x2, x3, or which is O x, y, z if you wish, but in tensor notation these of course must be x1, x2, x3, right. Now, whatever be it, these indices are attached to the components of the electric field vector. So, a general electric field vector pointing in some direction here, this is the direction of E, has a component E1 along the unit x1 direction, E2 along the unit x2 direction, and E3 along the unit x3 direction. So, the indices here, indices are the directions, are here the directions of the electric field vector. In other words, if I now take this coordinate system seriously, we also need a k direction, right. So, we have been using z for the propagation. So, z is x3 for us. So, let this be x and y, or x1 and x2 for the sake of this discussion, right. So, now since the wave propagates along z, the field can only oscillate in a plane perpendicular to this. So, if the field oscillates in a plane perpendicular to this, okay, I am struggling to sketch that, but let us put the oscillation of the electric field along the y plane. What does this mean? The electric field vector at every point ouch, let me nonetheless sketch this. We of course had a much better view graph of this much earlier in this course, and the magnetic field would therefore be perpendicular in a plane perpendicular to this. So, here the electric field vector E is simply E times x 2 hat or y hat, the way we have labeled our axes. It could well have been polarized, plane polarized along the x 1 or conventionally x direction, or we could have had E hat to be some E 1 times x 1 hat plus E 2 times x 2 hat, could have pointed along some general direction if we wished, yet along the xy plane or the x1 OX1 x2 plane, right. So, therefore, these indices, okay, correspond to the direction of polarization of the electric field. So, if you want to generate good second harmonic, choose a plane polarized wave to start with. You may have hope, because now you can imagine that when the beam is propagating with a polarization along the x axis, x1 axis, the refractive index it sees for not beam is propagating along the x1 axis, the beam is always propagating along the x3 or z axis. If the beam has a polarization along the x1 axis, then the refractive index that the beam sees is n1 for E x1 hat. The value of refractive index becomes n2 for beam polarized along the x2 axis. So, this is the square root of epsilon 1 this is square root of epsilon 2. For any intermediate direction of polarization, the value of the refractive index would actually depend on the angle that the polarization, the electric field makes with the x1 and x2 axes. We will figure this out going forward. Okay, we will figure this out going forward. Now, I still have not mentioned to you or brought you up to speed on what we mean by the ordinary and the extraordinary refractive indices. We will come to that as well in the next lecture, but at least we seem to be making some progress sorry, in reaching this condition of n1 or n at omega 1 being equal to n at omega 2. Okay. We seem to be making progress, right. So, I will stop here with a smile if you wish, because we have made some progress towards achieving phase matching. Okay. With that, we will close for today and we will continue in next week's lecture on Monday. Okay. For the live class here, of course, we can pause the recording. How do we achieve phase matching? It should be somewhat feasible for us to see that now. I want to do a spoiler here because you persisted with me this long. So, take the icing on the cake. Now, doing phase matching is not a problem. So, what is the problem? You had a normally dispersive medium. So, you had omega 1 here, you had, okay, these are the two values, n at omega 1, this is n at omega 2. So, you had no chance of matching these, correct. But now, think about it like this, you have you have the directions x and y. So, assume that this is, say, n, this is the frequency dependence curve for nx, alright, frequency dependence curve for nx. Now, all you need to find is a medium where the ny curve is kind of like this. So, that at omega 1, this was n1 at x, n1, n2 at x. Now, if this is the ny curve, ny at omega 1 is equal to nx at twice omega 1. You need to find a medium where this happens. That is, your pump is, say, if x is horizontal polarization, your pump is horizontally polarized, but the medium is such that for the second harmonic, if the second harmonic has vertical polarization, then the phase matching is achieved. Now, the way to think about this is, if you have such a medium and you put a horizontally polarized pump, of course, this is a crystalline medium. You orient your pump appropriately, your second harmonic will come out with a polarization perpendicular to the pump. It is not that you need to do something special, the medium does that for you. If the phase matching condition is achieved, you got the right crystal, you made it, you oriented it, you did all that, cut it, polish it, or you orient it, did all the things, put your crystal on a goniometer and did all the precise alignment, then all you need to do is launch the pump with the right polarization and the probe will come out being the second harmonic at a polarization, say, that is perpendicular to this in the example that I am giving you here. You see the point? You do not need to work anything more. For a pump polarized along x and a probe polarized along y, your crystal is phase matched, your medium is phase matched, your experiment is phase matched. So, this is what Franken did in his experiment. They understood and attained phase matching. They used quartz. Quartz is crystalline silica, crystalline SiO2 that does have N1, N2, N3. In fact, two of them, N1 is not equal to N3, but N2 is equal to N3 in such a medium. We will see about that. We would prefer such media. In that medium, phase matching could be done because polarizations matter. And this is how you are going to do phase matching for all lowered harmonics. It could be second harmonic, it could be third harmonic, whatever be the case. You just get the right crystal and the right this thing and polish. So, what do you do in a commercial second harmonic generation? You simply make sure that you cut the crystal and polish it in such a way that if your beam is incident normally, the k vector is incident normally, okay, and you mark an axis for the crystal cut, you say put your electric field along this direction. So, you would have a laser beam and you would have a half wave plate, you would rotate the wave plate so that the second harmonic, the pump beam has a polarization along the marked axis, you put the crystal and then you get the second harmonic out. The pump beam is along the preferred direction. So, you just cut and polish the crystal. You also have to measure the thickness of the crystal for other reasons we will understand better. So, if you do all that, which is what manufacturers do, so all you need to do is you or your PhD advisor has to pay for that, and then you get the crystal. So, you just place the crystal on a rotation mount, halfway plate, pump beam, out comes the second harmonic with its preferred polarization. That is all. So, that is second harmonic generation for you. We will see that, but that is all of harmonic generation relies on this type of phase matching. Alright, so we will see about this and a little more in the next lecture.